Okay, so this is 4.3, the gamma lesson, and we're going to start with example 5, which is on the bottom of page 209. And it's a parametric problem. We're going to deal with the first and second derivative in terms of parametrics and what that means. You need to have your calculator on your desk. And we're going to remind you how to draw this graph. What they're, this is meant to be a non-calculator problem. You're analyzing this, but we're going to back this up with the picture of the graph. Okay? So if you go here on your calculator, PAR mode, go to y equals, and type this in x1, y1. I put -1 in for the path where the particle is going to travel. That doesn't really matter. You can put a different. But this is the cubic that goes in x1. And putting in x1 is telling you this is going to travel horizontally. Put in y1, it would travel vertically. And we need a constant where it's going to travel. We're picking -1. You could pick +1 or something else. Just don't make it more trouble than it's worth. And then you can add x4 and y4 and turn it on. Okay? So we're going to draw the graph, and then we're going to go back and look at the work analytically. Make sense? So I push zoom 4, and there goes the particle. But then the purple graph is leaving a path, because that's what we turned on x4 and y4. See, we get a y equals, what's happening? Well, we can look at this graph right here and say cover up method. At time 0, the particle is going to start at -5. So we know it's going to start at -5. And we get down here to 4, where we put in the same thing that whatever's in x1. And what's in y4, which you should already have in there, but if you don't, is t. So the height is changing as per the time. And that's why it's leaving the path. It's not tracing over itself. So if we go back to the picture, and it's not going to draw the picture again unless you type over something. We'll go back up here, and I'll type over the -1 with a 1 again, push graph, and then I'll push enter, and that'll pause the part. So you see what could happen. It started at -5. It went to the right, coming back to the left right now when I paused it. Then what? Here comes the purple graph. Now, you just see how the particle went back to the right again? You have to make the window bigger. See where the purple graph goes back to the right. That make sense? So we saw that. This is just the zoom 4 window. So we go down here and make the Y max higher. I don't know, 8. There goes the particle. Here comes the purple path. You can see how it went back again. Okay? So what's going on? The particle went right, left, right. So how can we analyze that without the picture? And all we're doing is confirming stuff we did up till now in the same section. So we have a table here. Here's the cubic which is the position function, it's where the particle is. The derivative would be velocity. The derivative is going to be second degree. So I want to set this thing equal to 0. Well, the first thing I do is take out the greatest common factor, which is a 2. So if I take the 2 out, now this is just, right, this is algebra 1. I take the 2 out, I'm left with 3t squared plus a negative 14t plus 11. You want to find the zeros of that. Well, this is quadratic, second degree. It has 2 zeros. I mean, are real, 2 or not. We're going to see if we can factor this with a lattice. We have 3t squared and 11. Well, 11 is a prime number. The only thing that multiplies to 11 is 11 and 1. What multiplies to 3t squared? 3t and t. Now, we know these both have to be negative. Why? Because they have to multiply on positive 11, but the sum of these two terms has to be negative 14t. So the 3t can't get multiplied by the 11. That would give us too many t's. So the 3t's here, and t's here, ready? No, 3t here and t here. That gives you negative 11t and negative 3t, and they add up to negative 14t. So that's how I got this here. T plus a negative 1, 3t plus a negative 11. So what makes that thing 0? Well, 1 makes this factor 0. Set this equal to 0 and you get 11/3. We partitioned our number line. We go up here and say, all right, 1 makes the first derivative 0. 11/3 makes the first derivative 0. And this work in here is confirming the sign change. Here's my derivative. I go to the derivative and I put a 0 in there. Well, the easiest way to do it is here with cover up, and you would get a positive value, 22. Here's the 1. Well, 7/3 is a little awkward because that's what makes the second derivative 0. That's why it's in there. We'll just put a 2 in here. This would be positive. This would be negative. Positive times a positive times a negative. The derivative's negative. Go to the right of the 11/3. Go to 12/3, which is 4. Put a 4 in here. Positive, positive, positive. Right here, sorry. And then what's happening? This table right here for the first derivative is telling you what's going on. It's saying the particle is going right. You get the time 1. Then it's changing direction and going left. You get the time 11/3. Then it's changing direction and going right. Then what? We'll find the acceleration. So I find the second derivative, which is going to be linear. The only thing that makes this 0 is 7/3. 7/3 makes the second derivative 0. So what are we saying? Try and point over here. I don't know, put 1 in there. You're getting a negative. Decelerate. Put 3 in here, getting a positive, accelerate. So all of that information is in the table. You interpret the table after you set it up. You don't need to have a picture of the graph. You won't have it. Okay, this is a non-tabular question. Can you imagine this? Like, you never even saw. You use parametric mode maybe once or twice in pre-calc. Maybe to draw the unit circle. You didn't do parametric motion. Now you're asked to say, can you analyze parametric motion without the calculator? And you can. you take what you understand about the critical points for the first and second derivative, build the H chart. And again, this is the final copy of the H chart. When you do this, right, when you have a rough draft, you need to leave some space in here. Because how would you know that you're going to need space for 7/3 until you set the second derivative equal to 0? So you leave some room, or you do a rough draft. And the balance is, or the option is, here's the table, and then here's the number line, which partitions the derivative into the 3 intervals regarding the 2 zeros, 2 intervals regarding the 1 0. Okay? So, that's your model. You're going to go to problem 25. All right, so let's look at the picture for 25. You have this quadratic. We turn on X4, Y4. Push graph. Here comes the purple graph is going to confirm what happened. Okay? So you should be able to anticipate this now. If I look at this, what's in Y equals, you use the cover-up method at time 0, the particle is going to be 3 to the right. Then the derivative is going to tell us if it's going right or left. From the picture, we saw that it went left. So here's the table. The velocity function is linear. It has 1, 0, and 2. So the time 2 is when that changed direction. The time 2, the first derivative 0. Here's the sign change. It went left, it paused at time 2 and went right. And the acceleration was constant. Logical? No. No. I mean, is it logical the way this, you can analyze this without the calculator, is what I'm saying. Like you don't need to draw a picture. This complements what's in function mode. See, we can draw this in function mode, and you've got what? T squared plus negative 4t plus 3. Look what happened. It's the same thing, except it's not particle motion. At time 0, this is at 3. And instead of going left, it was going down, because the derivative was negative. And when you get to 2 to the right, that's where it stops going down and starts going up. And in parametric mode, at time 2, it stopped going left and started going right. And if you can merge what's going on in the 2 modes, you understand what's going on here, and then you make the step to doing this work analytically without the picture. Example 8. Ready? So example 8, we're in the textbook. It says, suppose you were to draw this graph freehand from the information they give you. Now, you're not going to have to draw a graph freehand in Math. But this shows your depth of understanding. Here's what they tell us. You want to draw this graph, and they're telling you about the first derivative. The first derivative is 4x cubed plus a negative 12x squared. Determine whether the extreme occur of f of the parent graph. Find the intervals where it's increasing and decreasing. Find the concavity, and then draw what this graph could look like. What did they do? You're looking at this. The greatest common factor that works here for the derivative itself, the first derivative is 4x squared. Think about this. It's a cubic. It has 3 zeros. How many were real? 3 were 1. In this case, it's 3, but 0 counts twice. Because you have this. 4x squared times x plus a negative 3. You have to count the 0 twice. That's a different graph than 4x times x plus a negative 3. So you have a double 0 here, and a 3. So you have 3 real zeros, counting the double roots. So what's happening? Because you have a double 0 here, there's no sign change. Now they have this table different than our H chart. But I think that's what you want to do. It's the same idea. Then what? We're saying using the table above, we see that the parent graph is decreasing from negative infinity to 3, and then increases when the first derivative is positive. Then the second derivative is a quadratic. The greatest common factor is 12x. What makes this 0? 0 and 2. Here's how they have the number line partition. To the left of 0, the second derivative is positive, so it's concave up. At 1, second derivative is negative. With 12 times a negative 1 plus a negative 2 is a negative 1. Concave down, to the right of 2, concave up. Said, okay, if I know that information, you could draw a picture of the graph. There's their picture. What do you notice about the picture? There's no axes here. Because you don't know where the axes are. Because all you have the idea of is the shape of the parent graph. Not what K is. It's where you have the shape of the cradle, but not where it sits in the can. Okay, now that would be, if you could do that, you're in really good shape. That's the highest level of section. You need to be able to draw the graph freehand yourself, which you won't have to do on today. It goes to, again, your depth of understanding. You can sketch this, and it works, you're in good shape. So, we're going to ask you to look at problem number 39. All right, so 39. We rewrote it. Just wrote the factor twice. So it's third degree. How many zeros does it have? 3. How many are real? 3 or 1. You see 2 because the 1 counts twice. But there's no sign change here. The sign changes at 2 from negative to positive. What are we saying? At 2, you're going to have a min. Why? Because the derivative is negative, and then it becomes positive. That's telling you the parent graph is decreasing, and then start to increase. So at 2, you would have a minimum of the graph. Then what? The second derivative is cubic, has 2 zeros. You take a lattice, you factor that, and the zeros are up 1 and 5/3. And you have 2 sign changes, which is confirming you have inflection points at 1 and 5/3. Ready? To the left of 1, the second derivative is positive, it's concave up. In between 1 and 5/3, it's negative, it's concave down. And to the right of 5/3 is concave up. Here's the table summarizing what you have. Here are the critical points. Ready? Critical points for the first derivative, no sign change at an input of 1. Critical points for the second derivative, sign changes. Okay, so if you're at home, I'm just reminding you, you have a quiz through 4-3. Your quiz, if you're at home, is going to be on Friday.